Since the beginning of civilization, we have looked towards the stars with amazement, curiosity, and eventually a humbling realization of how small we are. The observable universe is exceptionally large. To give you an idea, assuming an average of 100 billion stars per galaxy, there are 1 sextillion stars in the observable universe. That's 1 billion trillion stars. So just looking at our sun or our solar system doesn't tell us too much about the universe. And there's an awful lot to understand, from planet formation and planetary properties to physics and origins of our universe. An important way to expand our knowledge is through observing exoplanets. As Mary Wojtek, senior scientist and director of NASA's astrobiology program, put it, they spent years on researching the solar system and how planets formed. Now that we're observing exoplanets, we can determine whether or not we understood those processes even in our solar system. And what finding exoplanets does for us now is open up a vast exploration area to look for other habitable worlds. And how are we doing so far? Astronomers have discovered more than 3,200 other planet-hosting stars in our galaxy. To date, more than 4,000 exoplanets have been discovered and are considered confirmed. However, there are thousands of other candidate exoplanet detections that require further observations to say for sure whether or not the exoplanet's real. So, how does one discover an exoplanet? Well, there are a few techniques. There's astrometry, radial velocity technique, and transit method, which we will go over. But there's also direct imaging, microlensing, and more. Each have their own obstacles and advantages and sensitivities. In this video, I will cover the radial velocity technique and the transit method. Following those explanations, I will use my Lichess ELO dataset as an exercise to try and identify an exoplanet using each technique. Put simply, the goal is to learn a couple techniques used to discover exoplanets, see some of the methods in action, dive into the limitations, and understand how difficult it is to detect and confirm an exoplanet. Suppose we know that there are planets orbiting other stars besides our own. Well, it's generally very difficult to see these planets directly, given their stars are 1 billion times brighter than the planet. Instead, we can cleverly try and detect the planet by measuring the effect the planet has on its star. So it's easy to think about a planet orbiting a star and the star's gravitational effect on the planet. Newton's law of gravity shows us that gravity acts in both directions. So the planet also has a gravitational effect on the star. So what's actually happening is both the star and the planet orbit the center of mass of the system. Since both the planet and the star orbit the center of mass, the star takes exactly the same amount of time to do a full orbit as the planet does. So you can measure the star's period, and that'll tell you the planet's period. And then we can use Kepler's laws to find out how far away the planet is from the center of mass and calculate planetary properties like the planet's mass in units of its star's mass. And to observe the period and radius of the star's wobble directly is called astrometry. But think about how difficult that can be. What if the star doesn't move very much? This becomes even more difficult the further the star. This brings us to the radial velocity technique. Instead of measuring the star's position, we can measure the star's velocity. From the radial velocity curve, we can get properties like period, and then orbital radius, and then finally mass. But what would this look like? When the star is moving towards us, the light coming from it is a bit blue shifted, while when it's moving away from us, it's red shifted. So if we keep measuring how shifted the light is, we can figure out when the star has done a full orbit, and we get a graph that looks like this. So let's dive into this. So there's a few things going on here. On the bottom right, we're measuring the spectra of light, and we can see how shifted it is at any given point. On the bottom left, we have the planet's position relative to the star when we're looking at it kind of just like in our line of sight. On the left, we have an infographic showing how both the star and the planet orbit the same center of mass. And as I said before, because they orbit the same center of mass, we could see it takes the same amount of time for the star and the planet to complete one orbit. So if we measure the period of the star, we can get the period of the planet, and then through many other calculations, we can find out the mass of the planet. And on the right, this is the graph that we want. We want the radial velocity in meters per second of the star over time. The positive values on the graph correspond to the fact that the planet is moving towards us, and the negative values on the graph correspond to the fact that the planet is moving away from us. So if you just line it up, we can see that at the amplitude, the planet will be right here, opposite the star here, and if we're measuring the radial velocity, that's exactly the orbital speed, and we'll use that to our advantage. So we'll see later how we can attain a graph that looks kind of like this, and use that to calculate some planetary properties. But since we are measuring the Doppler shifts, the orbital inclination matters. Let's say instead of the planet orbiting like this, directly in line with our line of sight, let's say it orbited the star exactly perpendicular, so like this. Well, then the light wouldn't be red or blue shifted, and we couldn't use this method at all. Another limitation, since we're measuring the velocity in our direction, this may lead us to underestimate the mass of the planet, or even not be able to detect the planet at all. There's also atmospheric turbulence, light pollution, and water vapor, all of which pose strong challenges for ground observations. Even P modes, granulation, spots, and activity cycles can emerge as some of the stellar limitations that come with measuring radial velocities. Even if we get by all of that, we are still sensitive to more massive planets with shorter orbital periods, so we're missing out on a large collection of exoplanets. And the more massive planets have a greater effect on the star, making it easier to measure radial velocities. The shorter orbital periods make it more likely that you will observe multiple orbits in your data. For example, it would be very unlikely to observe a planet with an orbital period of 10 million days. Finally, there are even limitations that come with refracting telescopes. We want larger lenses to collect more light and resolve close objects. However, the larger the lenses, the harder it is to avoid defects in the lens. It becomes more difficult to retain the light, chromatic aberration becomes more pronounced, and larger lenses are harder to support. So let's say we get by all of those obstacles and detect a planet with the RV technique. How can we confirm it's actually there? How can we learn more about it? One way is to look for the exoplanet using the transit method. The transit method is a photometric method that aims to indirectly detect the presence of one or more exoplanets in orbit around a star. And there's a tremendous amount of precedence for this. For example, in 1999, the method was used to confirm the existence of HD 2094-58b, a planet that had been discovered almost at the same time by the radial velocity method. This one's a bit easier to understand. If you're looking at a star, and again, a planet passes in front of the star, instead of measuring the velocities, we can measure the apparent brightness of the star, and we expect the apparent brightness of the star to drop as the planet is transiting. And after the planet completes its transit, we expect the star's apparent brightness to jump back up to its pre-transit level. So we're looking for something that looks like this. And what does this tell us? Well, we can find the percentage of brightness blocked by the planet's transit and use that to calculate the radius of the transiting planet in units of its star's radius. So similar to how we needed the star's mass in the radial velocity technique, we need the star's radius to solve for the planet's radius using the transit method. But the transit method has its obstacles too. Some obstacles include the fact that the planet doesn't transit at all. Let's say its orbital inclination again is exactly perpendicular to our line of sight. We would never see it transit. If the planet is too small, then the apparent brightness may not drop. In the same vein, what if the star is too big or too faint? More problems may emerge if the star is too variable, making it difficult to isolate transits in your data. For these reasons, the transit method is also sensitive to more massive planets with shorter orbital periods. So as an exercise, let's try and detect an exoplanet with the radial velocity method and confirm the detection with the transit method. And what dataset will we use? I thought it'd be fun to use my Lichess ELO over the past 300 days. Why did I think this would work? When I play chess online, I constantly try new things, take dips in my ratings, And then some days I'm an absolute engine, and I gain it all back with sometimes more. For these reasons, the graph looks something like this, which kind of looks similar to what we're looking for with a radial velocity dataset. Here's a comparison. So let's use this as a mock dataset for a star's radial velocity, and then again with a trick, we'll use it as a star's flux dataset, and then we'll try and confirm it with the transit method. So let's begin. Okay, so we have data of my chess rating over time. We have 300 days, and the goal here is to try and look for that sinusoidal fit for a given set of periods. So I chose to test periods of length 1 to 60. We're going to calculate a periodogram. So a periodogram calculates the significance of different frequencies in a time series data to identify any intrinsic periodic signal. So we're going to define a function called Lomb Scargle Fast, and we're going to search this data for any periodic signals, and then from there we're going to jump in Excel and try and fit a sinusoidal function to it as best we can, and then try and get some planetary properties from that. Just defining the function, and it's going to spit out this periodogram that we want. So it's 1 through 60, the signal of each of these periods. So we see like up until like 8, there's absolutely no signal. There's some signal for a value over here. The best period winds up being 46 days. So we're going to hop in Excel and try and fit a sinusoidal curve to this function with a period of 46 days. All right, so we got the period is 46 days from the periodogram, and we want to fit a sinusoidal curve to the test data, and we did exactly that. We can see that there is a slight periodic signal here, specifically in this first, third, fourth, and then perhaps sixth. We use this equation, and we attain these values. And now we're going to move over and grab the period in days. And then for other equations, this is what it is in seconds and then years. The orbital velocity is just the amplitude. If we remember the GIF that I was showing before, when its radial velocity component is directly facing towards us, well, that's just its orbital velocity. And then we could use the orbital velocity and the orbital period, assuming a circular orbit, to find the orbital radius. So now that we have the orbital radius, and we have the orbital period, all we need is the system's semi-major axis to find the orbital radius for the planet. So how are we going to do that? Well, we have Kepler's law, which says that if you include kind of this prefactor, which is g times n over 4 pi squared, then you could find a relation between the period and the system's semi-major axis. And that value is going to come out in meters. So this is what it winds up being in astronomical units. But we're going to use the period, we're going to use the meter value because that's what we have our orbital radius in. And then what's the orbital radius for the planet? Well, it's just our system semi-major axis minus the orbital radius for the star. And now that we have the orbital radius for the star and we have the orbital radius for the planet, and we're assuming for both this and the transit analysis that the star that we're looking at is a sun-like star. So we're going to use the mass of the sun, and then we're also going to use the radius of the sun for our next analysis. So we have the mass of the star, we have the orbital radius for the planet, and we have the orbital radius for the star. So now we could just use the fact that they both orbit the same center of mass and find an equation like this, where the mass of the planet over the mass of the star is equal to the orbital radius for the star over the orbital radius of the planet. So the planet's mass is about 8.5 thousandths of the star, which is about this many kilograms. And then let's just put that into units that we could really understand. So I grabbed the mass of Jupiter and grabbed the mass of Earth. So this is the equivalent to about 9 Jupiter masses, or about 2850 Earth masses. So that's a very large planet. And let's try and confirm this with the transit technique. We want to try and confirm the detection of an exoplanet that we found with the radial velocity technique. So now we're going to be looking at what if this data was the flux or the luminosity with respect to the surface area of the star over the time period of 300 days. So now instead of the sinusoidal function, we're going to be looking for a periodic dip in the signal. And we want to say, like, okay, is there a significant periodic dip to where we could say there's a planet transiting this star, and that's why its apparent brightness or its flux is decreasing. So what are we going to do? We're going to do the same thing. We're going to try and calculate a periodogram, which again tests the significance of different frequencies in a time series data set, and it's going to look for intrinsic periodic signals. So we do the same thing on a different data frame. And we find that the best period is also 46, so that's great news for us, but also no surprise. The data is the same. The only thing that we did here was to try and make it more like some flux data over time. It wanted to be centered at 100% of its luminosity, and then each dip will correspond to like a percentage dip that the apparent brightness takes when the planet transits the star. So we wind up doing the same process with the different data set, and we wind up finding that it has the same period with the greatest signal at 46 days. So then we're going to hop in Excel and do some stuff to the data there to try and see if we can find a transit. Okay, so now we've detected an exoplanet with about 9 Jupiter masses, and we hopped in to R to compute another periodogram on the flux over time of the star, and we're going to be looking for transits. And then from there, maybe we can calculate the radius of the planet, maybe the density. The first step was we have the same data, but we want it to look a little bit more like transit data. So we fit a 4th degree polynomial, divided out, and we get a curve like this. This is now the flux adjusted. And then we put that in the periodogram. We got the period equals 46. So instead of fitting a sinusoidal curve, now we're going to be looking for, can we capture at intervals of 46 days these dips in the flux over time? And we want the same dip. So what do? We try and find however many folds that we can about 46 days. So we pick different starting points and then go from there. I found that this was probably the best starting point. So I created 6 different series. Every 46 days is a new curve. And that's what's plotted down here. So each one of these different colors is a different folding or a different transit. And as you can see, it's very messy. So I took the average of all of these curves, and that's what's plotted over here. So we have the flux over time, the average flux over time for these 6 transits. And the graph turns out to look really nice. As you can see, it's pre-transit levels right around 100% flux. And then we have this strong dip as it transits inside of that period. Let's compute what that dip is, and then from there, we can calculate what the radius is, and then we're going to be able to see what the density of the planet is as well. So I took the average of these values and these values, all the pre-transit levels, and I subtracted the average of these values in the dip to find that it took about a 2.5% dip. Now I can take the square root of this value and find that the radius of the planet is about 0.16 solar radii. And we know the radius of the sun. So now we can calculate that the radius of the planet is about 113,000 kilometers. But what does that mean? It's about 18 Earth radii or 1.5 Jupiter radii. So now we have an exoplanet that we detected with the radial velocity technique, confirmed with the transit technique, with a mass of about 9 Jupiter masses and 1.5 Jupiter radii. And the density winds up being a little less than double what Jupiter's density is. So we can assume that it's mostly made out of gas. It's probably another gas giant like Jupiter. It could have a little bit more dense materials. Maybe there's some rock substances on the planet. Maybe there's a different composition there, but it's hard to tell. So I took periodic chess data and tried to treat it like some stellar data in two different ways and detect and confirm a planet using these two methods. I hope you guys liked the analysis. I hope you guys learned something. Have a good day.